Variations and applications. Our objective here is to find equations of direct, inverse, combined variations given values of the variables. We're going to solve applied problems involving variations. If a situation gives rise to a linear function where f of x is equal to k of x, or kx, or y is equal to kx, where k is a positive constant, we say that we have direct variation, or that y varies directly as x, or that y is directly proportional to x. The number k is called the variation constant, or constant of proportionality. Okay, so the graph of y equals kx, where k is greater than 0, so meaning it's all positive numbers, always goes through the origin, and it rises from left to right. As x increases, y increases. That is, the function is increasing on an interval of 0 to infinity. The constant k is also the slope of the line. Now, find the variation constant in an equation of variation in which y varies directly as x, and y equals 32 when x equals 2. So we get this order pair here, and we're wanting to solve for what is the constant. We know the order pair, but we don't know the constant. And again, they said that k represents the slope of the line that we're working with. So plug in 32 for y and 2 for x. And now we have 32 is equal to 2k. And let's solve for k by dividing by 2. So k is equal to half of 32 is 16. So now my variation constant is 16, and it's the rate of change of y with respect to x. The equation is written as y equals 16x. So let's do our next one. Water from a melting snow. Okay, so water from melting snow. The number of centimeters of water W produced from melting snow varies directly as S. The number of centimeters of snow. The meteorologists have found that under certain conditions, 150 centimeters of snow will melt to 16.8 centimeters of water. To how many centimeters of water will 200 centimeters of snow melt under the same conditions? So the underlying question is, and sometimes it helps if you can draw a picture. Sometimes it helps if you can label. How many centimeters of water will 200 centimeters of snow melt under the same conditions? Okay, they told us what W is. W is going to be the water produced from this melting snow. Said S, the snow varies directly as S. Okay, so we know what those are. We are giving, the meteorologists have found under a certain conditions, 150 centimeters of snow will melt to 16.8 centimeters of water. So these are very important parts to help us solve this. So what we want to do is we want to write our formula out, which they've already given it to you here. And we're going to apply the K constant. That's our variation constant. So now I got W, whoops, let me write a little neater, my apologies. So I have W of S is equal to K of S. What do we know? Well, we know what S is. S is going to be the conditions of the snow that will melt, because it said snow varies directly with S. So I'm going to plug in everywhere as I see S, the 150. Okay. And then it said that W was the water that produces, or centimeters of water that produces the melting snow. And they told us what that was here, which is 16.8. So I'm going to rewrite this one more time, because W is that. S is just saying W of S. So this here is going to be written as 16.8 equals the K of 150. Now, I want to solve for K. In order to solve for k, we have to get a coefficient of positive 1 on it. I have 150. So that means I'm going to divide because division undoes multiplication. I'm going to rewrite it where it's a little bit neater. Now, if you just be careful, if they're asking for the variation, be sure and read what it's required of you to round to. And be careful because sometimes you need to leave it in fraction form when you plug it back into your work because you might not round into the very end. If you round too soon, you can end up having an answer off by thousandths or hundredths of a point. I'm going to go ahead and write this in decimal form because we're solving for the constant k here. And I get, oh wow, that came out nice and pretty. I get k is equal to 0.112. So that is my constant. So I can rewrite it back down here. W of S is equal to 0.112 S. So now I have my model. I got my model from this. And here you go. Here's a image. So if you could draw, if you're a really good artist or close, draw this. This will help you. But be sure and label. All right. So now let's go back. Let's go back to that question. The very last part said, so we had to come up with our model, right? You had to get that in order to solve the last part. How many centimeters of water will 200 centimeters of snow melt under the same conditions? So we got our formula here. We got a diagram here that we can look at. Now we're going to plug in, because it said snow, right? 200 of melting snow. Remember, S was my snow. So I'm going to take my formula, and everywhere I see 200, and plug in 200. So that gives me W of S, which is W of 200. And let me fix that S there. I'm just putting W in. So we're going to multiply that 0.112 times 200. And we're going to get 22.4 centimeters. And that answered our question of water. So, and this is right here is a really good statement. Whenever you do application problems, you need to be able to make statements that are clear and understandable. If a situation gives rise to a function, f of x is equal to k divided by x, or y is equal to k divided by x, which makes sense, right? Because f of x yields y. So the notation, either one is correct. So now again, it said we had k divided by x, where k is a positive constant. We say that we have inverse variation, or the y varies inversely as x, or that y is inversely proportional to x. The number k is called the variation constant or constant of proportionality. For the graph where y equals k divided by x, k is not going to equal 0 in this one. As x increases, y decreases, which makes sense because now we're talking about fractions, right? That is, the function is decreasing on the interval of 0 to infinity. And you notice it does not include 0 because it's a fraction. All right. So now we have graph of y equals k divided by x, where k does not equal. Here is a graph of what it would look like. So it says find a variation constant and an equation of the variation in which y varies inversely as x and y equals 16 and x equals 0.3. So we're going to do it the same way. We're going to plug in what we know. So we know 16 for y and k divided by that x. Well, to undo this fraction, we want to undo the denominator. That means we need to multiply, right? Both sides by that 0.3. So now that I got K times 16, or excuse me, K is equal to 16 times 3.3, we get 4.8. That would be our constant here. So my model, my equation here would be this. Okay, now filling a swimming pool. The time T required to fill a swimming pool varies inversely as the rate of flow R of water into the pool. A tank truck can fill a pool in 90 minutes at a rate of 1,500 liters per minute. Okay, so we're going to go ahead and underline that. It says, how long will it take to fill the pool at a rate of 1,800 liters per minute? So T is for time, R is for the rate. So what we're going to do is we're going to plug in what we know into this formula. So I got T of R is equal to K over R. And we know what the time is. They said that the tank truck can fill the pool in 90 minutes. So that's T. My R, they said, has a rate of 1,500 milliliters per minute. And now we got to solve for K. Well, in order to undo the fraction, I'm going to multiply both sides by the denominator. So now I have K is equal to that 90 times that 1,500, which gives me 135,000. Okay. Our minutes reduced, should left it with R, but this is our variation. So next, what I want to do, well, let's go ahead and write our formula out, our model, our equation. This is what we got right now to work with. That's what we want to do to solve for the next part. So when I take that next part, let's go back, and it wanted to know how long will it take to fill the pool at a rate of 1,800 liters per minute. So I'm going to take this next screen. I have T of R is equal to that 135,000 divided by the 1,800. And when I do that, now I get time of 75. So this will take 75 minutes to fill the pool at a rate of 1,800 liters per minute. All right. Now we're going to determine whether direct variation or inverse variation applies. We're going to write an equation of the form of y equals kx for direct variation, or you can say y divided k of x. So we got a multiplication or a quotient. And for inverse variation, substitute the known, the unknown values, and solve for k. So we're going to do just like we have been. We're going to write our equation of a variation and use it to find the unknown values of the problem. Now, other kinds of variation. Y varies directly as the nth power of x if there is some positive constant k such that y equals k times x raised to n. Y varies inversely as the nth power of x if there is some positive constant k such that y equals k divided by the n or x raised to n. Y varies jointly as x and z if there is some positive constant k such that y equals k times x times z. Okay. So now we want to find the equation of variation in which y varies directly as the square of x when y is equal to 12 and x is equal to 2. So we're just going to plug it in our formula here. And now we have this, and then solve for k. So we're doing what we have been the whole time. So now we have our model. Okay, so that's what we want to work with. Now next, it says find the equation of the variation in which y varies jointly as x and z and inversely as the square of w. So And y equals 105, x equals 3, z equals 20, and w equals 2. So we have this, a lot more going on. We have this equation here. And we're just going to plug in what we know. 105 for y. We don't know what k is because it's what we're solving for. 3 for x, 20 for z, and then w is 2, and we're squaring it. So let's clean this up. 105 is equal to k. 3 times 20 is 60. 2 squared is 4. Now let's clean it up just a little bit more. And if you can reduce that 60 and 4, I would reduce. Always reduce, make it easier. If not, just leave it alone. But 4 goes into 60 15 times, so that's going to make it a lot easier. And now I want the coefficient to be positive 1 on k, so I'm going to divide by that 15. And now I got k is equal to 105 divided by 15, and that gives me 7. So my constant here is 7, so I'm going to write my model out. And this is what we want to work with. Okay, so let's talk about our next one. It says application of volume of a tree. The volume of a tree, or excuse me, the volume of wood V in a tree varies. So we're going to use V, varies jointly as the height h and the square of the girth g. Girth is the distance around. So we're talking about a tree now. If the volume of the redwood tree is 216 meters cubed, when the height is 30 meters, and the girth is 1.5 meters. What is the height of the tree whose volume is 344 meters cubed and whose girth is 1.6 meters? So what I'm going to do is use our volume formula. We got V equals K HG squared. And again, we are talking about it varying jointly. And we got to figure out what K is, but we know what V is. V, again, is the volume of the tree, and the volume was given to us right here. So we have 216 meters cubed. K. And then H, our height, was given to us 30 meters, and then our girth was given to us 1.5, and we're squaring that. So now what I would do is I would say, okay, 1.5 squared, and then times that to 30, and we're going to get a decimal here. So I got 216, 67.5K, and then we're going to divide by that 67.5. And now I know what my K is. Let's divide that out right quick. 216 divided by 67.5. It gives me 3.2. So K is 3.2. So I know my constant. Now I could do the next part. The next part says we have a volume of 344 meters cubed and a girth of 60, or excuse me. Yeah, it wants to know what's the height of the tree. And we have a girth of 1.6 meters. So our volume is 344. And we're going to set it equal to 3.2 times H times that 1.6 squared. So what I would do is I'd clean up this one side first. I have 1.6 squared times that 3. I believe was it 3.2. Yes, that's what we got for our constant K. Then we get 8.192H and divide by that. So now I have H is equal to and depending on where they want you to round to, I'm going to round to right now nearest hundreds to see what it wants. And don't forget your unit and what the height is measured in meters. So it'd be meters. Let's see what the end answer is. Okay, they rounded to the nearest whole number, so that makes sense. Thank you.